Okay, welcome everybody. Our next talk is by Francesco Costa from IPNP, Charles University, Prague, Czech Republic, and he's going to talk about low reheating temperature in context of freezing dark matter. So maybe I'll send you a reminder when 5 minutes are left.
Perfect. Thanks for the invitation, first of all. And yeah, so I'm going to present a series of works that I've done with my collaborators that you can see here on the screen. And they are in the context of low reheating temperature for freezing dark matter. Okay, so this is the outline. So I'm going to give a brief introduction on freeze in and freeze out, and then discuss some of the problems related to the freezing. And then see how at low reheating temperature we can solve some of these problems, and we also can get some very interesting physics. And then if I have time, I will discuss temperature evolution during reheating. And please feel free to ask me questions also during the talk. I think that's quite nice, and you can clarify various points. So let me start with the introduction. So as you probably all know, when we have freeze out, we're talking about a dark matter production mechanism where the dark matter is in thermal equilibrium with the standard model. So it follows the equilibrium distribution. Here is the black dashed line. Until it doesn't, which is when it freezes out. And to study that moment, we need to study the Boltzmann equation, right? So we have, in this case, say this is the evolution with time of the number density n dot. Then we have the Abel dilution because we're in an expanding universe. And then if we have production of the dark matter, we have a rate of production gamma. So from the standard model to the dark matter, and then we have a back reaction when the dark matter annihilates back into the standard model. So we're reducing the number of dark matter particles. Okay, this just also to set some of the nomenclature that I will use. And the interaction on the right-hand side is relevant as long as this is bigger than the Hubble dilution that we have on the left-hand side. When that's not the case, then we have what we call the freeze out. So the dark matter doesn't follow the equilibrium distribution anymore, and it just remains constant. The yield is constant. And the stronger the coupling, the longer we are staying along this equilibrium line, and so the less dark matter we have at the end. And this is all pretty standard for the freeze out. One nice feature that I want to mention is that we have an independence on the initial condition because of the thermalization. So we don't care what happened very early time because everything is thermalized, and the number density at this time here is just fixed by the temperature. Okay, and something that I will carry on through the presentation is the study of one specific example, which is the Higgs boson dark matter. So in this case, we have a dark matter that we can call S, this new field that we introduce, and we introduce this symmetry to make it stable and not decaying. And if we have the scalar field, then we have a Higgs boson interaction with the standard model Higgs, which is this is the Lagrangian term that we have. And if the coupling is big enough so that the new particle S is in thermal equilibrium with the standard model, then we can have production via this mechanism, the freeze out. This is the plot of what it looks like. This has been studied many years ago and is still relevant. So here we have the coupling and the mass in this plot, and the red line is the value of coupling and mass that give us the correct relic abundance. That means we can reproduce the data that we have for the dark matter. And all the colored lines or like areas are excluded by experiment. So this plot is already some years old, but the experiment just got better and better. So pretty much this model is excluded apart from like the tip of the depot that you can see in the plot. And this is true for a lot of other freeze-out models, at least the one that are just very simple and with one dark matter candidate. As soon as you start introducing maybe 2 dark matter candidates, then you can still are still allowed from the experiments. But since some of these simple models and the one that maybe were more expected as well, maybe also connected with supersymmetry and so on, were not found at direct detection, then people also started thinking about other direction and other production mechanism, like the freezing, which just removes one of the assumption of the freeze out and studies the production mechanism in a different regime. So we're not anymore in equilibrium. Now we assume that the dark matter never enters the thermal equilibrium with the standard method. This adds a dependence on the initial condition, because if something is produced very early before the freezing kicks in, then that will stay around because the dark matter is not in thermal equilibrium, and so everything that's produced at any point in time during the evolution of the universe just piles up, so it sums. And in general, this requires very low coupling, both to avoid thermal equilibrium, but also to get the correct periodic abundance, the coupling is pretty low, order 10 to the minus 10. So if we have a look at the Boltzmann equation, the same as we saw before, the forward production, so the production of these scalars, this goes as the number density of the Higgs squared, while the back reaction goes as the number density of the dark matter squared. And since we have to assume a negligible initial abundance, so that the actual production is driven by the freezing, then this second term normally is neglected. And so then you can rewrite the Boltzmann equation in terms of the yield and the temperature, and then you have just a simple integration in the temperature instead of having a differential equation. So that's pretty simple to solve, and you can get the correct periodic abundance for the case of the Higgs boson at 10 to the minus 11 for the coupling, and no dependence on the mass. Something to notice, though, is that here we are still having an underlying assumption that's not often made explicit, which is that the reheating temperature is much bigger than the mass of our particle. In fact, normally one integrates from 0 to infinity because we assume that the highest temperature that my thermal bath reaches is very high. And since this is infrared dominated process, we can just push this to infinity. But if the highest temperature of my thermal bath is actually smaller than the dark matter mass, then this is not a correct approach anymore. And we'll come back to this later. Okay, here just to show you the behavior of the freezing production. As you can see here, the yield is always much below the equilibrium yield, the dashed black line, and it increases like the coupling squared. So we have this increase in behavior now, which is the opposite as we had for the freeze out, where the yield was decreasing with the coupling. And the production normally stops around the value of the mass of the dark matter. So let me put them together in one plot to see what's happening and to have like some numbers in mind as well. So on the y-axis, we have the relic density, so the amount of dark matter that we have today, and we need to reproduce the observation with this, which is around 0.1. And on the x-axis, we have the coupling. So as you can see, for the freeze out, let me start with the freezing. As we just said, the number density increases quadratically with the coupling. So higher coupling means we have more dark matter, while for the freeze out is the other way around. Lower coupling means we have more dark matter. And the freeze out, the standard coupling that makes freeze out work are around weak coupling, so 0.1 to 1, let's say, while for the freezing, as we said, 10 to the minus 10, 10 to the minus 12. So there is this big region in the middle where the coupling are either too big or too small for the two production mechanisms, making such that the dark matter that each of these production mechanisms produce is too much. So none of the two work in this intermediate regime for the coupling. And this is quite a huge window, which is like 10 order of magnitude window, where both regimes produce way too much dark matter. Okay, so we can keep that in mind as well for later. Okay, after this introduction, let me motivate why we want to study low reheating temperature, apart from the fact that it's an allowed regime and it is interesting and it was not explored so much before we started dealing with these issues, but also because, as we will see later, it can address one of the problems of the freezing. So as I was saying, freezing tends to have a very small coupling to the standard model, or the 10 to the minus 10 to the minus 12. And these couplings make such that the freezing models are very hard to test, especially in direct testers. It's normally much easier if you have a mediator, so maybe you can test the mediator, but if there's no mediator and you have just such tiny coupling, then they are very hard to observe experimentally. And then we have an issue, which is the gravitational particle production. So as I was saying, like normally when freezing is studied, you assume that you have an initial negligible abundance. So you assume that we start from a very low number density when freezing kicks in. So freezing is the main mechanism that produces the dark matter. However, we always have some background gravitational production of dark matter. So let me give you one example here. So imagine you have a scalar and we assume a basic assumption. So this scalar is not coupled to the inflaton during inflation. It's just there. But of course, it couples gravitation as everything does. And during inflation, the quantum fluctuation of this scalar around this minimum can be described by a probability distribution. And this fluctuation, as it has been studied, and here there are some citations, but there's lots of more work on this, they grow, they get amplified during inflation. This fluctuation, they get stretched, and then finally, the scalar behaves as a condensate, which is effectively a matter content in the universe. So this scalar can behave as dark matter. And here in the plot, you can see that the yellow region is where we produce the scalar, but we overproduce it. So this is more than the observed dark matter. And here I plotted for us quite standard value of the Hubble rate at the end of inflation of 10 to the 14. So in this region, we overproduce dark matter just through this gravitational production. And the red region, the dark matter self-thermalizes because the self-coupling is too high. And so we're not interested in that region because it would be not a free scene anymore, right? Because we have a thermal dark matter. And people have studied this option as one option to actually produce dark matter. So if this can produce so much that the standard parameter space of dark matter, let's say the Wien parameter space of dark matter, is already excluded. You can see here masses around GV and TV, it's all excluded. Then you could say along this line, right, here we get the correct radical abundance. However, to do that, it means that you also have to trust that this approximation that we're doing is correct, meaning that the theory of gravity that we're using to doing this computation is actually the theory of gravity that works at this very high scale. And this could be problematic if, when we get to a quantum gravity theory, if this produces a big correction. And that might be the case since we are talking about scales that are closer to the Planck scale. However, there is a way to rescue freezing and to avoid this overproduction from the production during inflation. So this in this picture, there is an assumption which is the instantaneous freezing, meaning right after inflation ends, at age end, we get that all the energy from the inflaton gets dumped into the standard model, and we produce the standard model thermal bath. So we have the reheating here. However, it's quite normal to have also a so-called reheating stage. So maybe the inflaton doesn't decay all instantaneously, but it will take some time. So we'll have a matter-dominated epoch, for example, if the inflaton is oscillating around its squared potential, quadratic potential, and that will dilute part of the relic density that was produced during inflation. And now we'll see it in a second why. This can also be done by any exotic matter domination. So if before radiation domination we have some matter domination, even if it's not the heating stage of the inflaton, we still get some dilution of the number density that was produced during inflation. And here we can see it quite clearly. So you see here we have the instantaneous reheating on the left, and then where we have a reheating stage on the right. And here I'm just computing the number density as some late time in the two cases. And on the right-hand side, this late time is before radiation domination. So it's a bit simpler. But as you can see on the left-hand side, this goes as the ratio of the two times, time at the end of inflation and the late time to the 3 hours, while in the second case to the square. And therefore we get a smaller number density of this end, which is the number density that we have of this scalar field at the end of inflation, if we have a matter dominated epoch. So we get this dilution of the number density if we have matter domination. And we can have an idea of the scales that we need in order for this to know how long this matter dominated epoch needs to be, or how low the reheating scale needs to be in order to get rid of all the previously produced dark matter. So we define this delta NR, which is just the ratio of the Hubble at the end of inflation and the Hubble at reheating, and the square root. And you can imagine this as the ratio between the temperature that we would have with instantaneous reheating at the end of inflation and the actual reheating temperature that we have. And if we ask to avoid overproduction, so omega h squared needs to be smaller than 0.12, then we get an expression of this type. This is for the production that I described before, the one where the stochastic oscillation of the scalar field were stretched during inflation, right? So in this case, we get a lower bound on delta NR. So to get rid of all this previously produced dark matter, we get a lower bound on delta NR. So we can plug in some numbers. So H and as before 10 to the 14 GeV, a mass of 10 TeV, and a self-coupling of the order 10 to the minus 10. So we're still in this feebly coupled universe, let's say. And so for that, we see that we get this huge delta NR. So we really need a very long matter-dominated epoch, or a very big hierarchy between H at the end of inflation and H at reheating. And so this would mean that naively, we could expect the temperature at the end of inflation to be 10 to the 15, but the actual reheating temperature is then 10 to the 3 GeV. So we can get a very big hierarchy of scales, the scale at the reheating and the scale at the end of inflation. And this means that my scalar has been oscillating for a very long time and keeping this matter dominated equal for a long time, meaning that the coupling or like the decay rate to the standard model is relatively small. The production during inflation is not the only production that can happen before freezing. We also have production during the inflaton oscillation. So during reheating, you can also produce this dark matter, even if it's not coupled to the inflaton. And so we also computed the lower bound on delta and R coming from that, but you can see more details in the paper if you're interested. So just to summarize this first part, we said that we need this long matter-dominated epoch so that we can dilute all the early relics that we produce, and we can pretty much rescue freezing. So we again make make freezing finally independent from the initial condition, as which is or like we satisfy this requirement of freezing to have negligible initial abundance, which is not straightforward otherwise. And this implies that the reheating temperature is low, as we saw before. It can be quite low in order to remove all these originally produced relics. So apart from this, then as we were saying before, the low reheating temperature is also just an allowed regime because we know that the only bound that we have is from BBN, which says that reheating temperature needs to be bigger than some MeVs. And as we will see later, this makes our freezing dark matter testable, way more testable than otherwise. And also, it's a new regime. I mean, nowadays we have there has been many works, but it's still like a new regime that one can test. So let me see. Let me try to show you what happens when we have freezing at low reheating temperature. So in this case, we still stick to the Higgs volta and the scalar dark matter because it's very easy and we can see it quite clearly. And with low reheating temperature, now I mean exactly that the reheating temperature is lower than the mass of the dark matter. So as you know, if the Higgs is in thermal equilibrium with the rest of the standard model, then it has a thermal distribution, which is peaked around the temperature of the thermal bath at that point. So if the reheating temperature is the highest temperature, then we have the number density is peaked here. But if this is lower than the mass of the particle, then all the Higgs particle that have this energy here will not have enough energy to actually produce dark matter. And only the particles in the tail of the Boltzmann distribution will have enough energy to produce my particle S. And therefore, the rate of production becomes Boltzmann suppressed because we can only pick out the tail of the Boltzmann distribution from all the Higgses that we have in the thermal bath. And so if we go and do the integration as before of the Boltzmann equation, the integration in the temperature, we still neglect the back reaction. Then we see that now we get, as before, 3 times 10 to the minus 11 for the coupling. That gives me the correct rate abundance. But now this coupling is exponentially enhanced. So this Boltzmann suppression translates in an exponential enhancement of the coupling, meaning that depending on the ratio of M, S, and T, R,
Hello? Hello?
You see him? Hi, I'm sorry.
Yes.
I think my computer froze. Do you hear me now?
Yes. So your computer went outside the Hubble horizon?
Okay, let me just grab my presentation again. Sorry, I needed to swap laptop. That happens sometimes when I use Zoom. Not sure why. Okay, give me just a second and I'm there. I can share it.
Yes, we can see.
Okay, sorry again for the interruption. Let me go back to where we were.
Sorry.
So I guess we were here, right? When
Yes.
we did, yeah, okay. So yeah, as I was saying, now the coupling can have this announcement. So the production rate is boson suppressed, but the coupling can be exponentially enhanced. So from the 10 to the minus 11, which is the standard freezing, when the reheating temperature is very high, then we can go to much higher couplings, if depending on the ratio between the mass and the reheating temperature. But if the coupling keeps going higher and higher, at some point we'll need to take into account the back reaction. And when we take into account the back reaction, there is a small part of the parameter space where the back reaction is important. And then the two rates, actually the forward production and the back reaction, becomes equal. And so we are again in thermal equilibrium and we are back to a freeze out. Okay, but all of this can be shown also in a plot. So as I was saying, we can keep growing with the from 10 to the minus 11. We can keep growing with the coupling given by the ratio of the mass and the reheating temperature up to when we hit the freeze out coupling. And at that point, the dark matter is in thermal equilibrium and is produced by a freeze out. So the freeze out coupling is the upper bound for each mass. And then there is it's in thermal equilibrium again. So that this is the same line that we saw in the freeze out or in the WIMP plot at the beginning. And now we can draw these lines that once we fix a reheating temperature. So here we have reheating temperature of 120 GeV, and we can draw this line where we get the correct relic abundance. So on this line, we get omega h squared around 0.12. And along this line also, the dark matter is not thermalized, so we are still in the freezing regime, like we still are non-thermal. For lower masses, then it's a bit harder to get an analytical expression, but we can numerically solve it quite easily as well. And we get a very similar behavior because the main feature of this is this exponential suppression of the interaction rate. And something interesting now, you see that, the more reheating temperature that I choose, the more benchmark of these lines we can get. So we can populate all the parameter space below this freeze out line for different reheating temperatures. So all this parameter space below is available for this freezing at stronger coupling. And of course, there are experiments that probe freeze out, and therefore they're also already probing this freezing because they, as we saw before, they push already below the freeze out line. So they are testing all this parameter space that's available for the freezing. So we have the direct detection experiments. And as we know, they will push with the next generation towards the neutrino fog line. So we have more, we expect to go and test all this region as well between the current experiment and the neutrino fog. And we also have LHC and the future colliders if they're going to build that. So we have possible signals that we can expect from this dark matter, apart from the fact that it's already tested with current experiments. And so you can see here, I just populated the plot with more lines with more different reheating temperatures. And we can see something very interesting that I haven't pointed out yet, that reaching up to this freeze out line means that the freezing can be realized up to coupling order 1, as you can see. While I remind you that the standard freezing is realized at coupling 10 to the minus 11. And it's testable and it's been tested already. Another interesting feature is that imagine very low down here at 10 to the minus 11, we have the freeze-in line, which is just 10 to the minus 11. And then we have these different lines if we move the reheating temperature to lower values. So this means that we have, if the reheating temperature is lower than the mass, then we have the possibility to get the correct radic abundance for any coupling in between, given the correct ratio of masses coupling and reheating temperature. So we can populate all this region that was not, that before was not possible was not giving the correct radic abundance. Here, just to show you just very quickly, like a snapshot of what happens very close to the freeze out line, which is the purple line. Here you can see that the back reaction starts to be important, and the line doesn't go just straight upwards, but it curves and merges into the freeze out line. And it's also quite interesting because here the dark matter is also not yet thermalized. In fact, the rates are still different, and then as soon as they are the same, then we go into the freeze out line. And this is the plot that I showed at the beginning with the freeze out on one side and freeze in on the other side, and in the middle, this 10 order of magnitude overproduction gap. And what's interesting now is that in this parameter space for this coupling, actually we can produce dark matter with the right relic abundance if you choose the right reheating temperature. So these are lines for different reheating temperature with a reheating temperature that increases, and when we get to infinity, then we get back to the freezing. So all this parameter space that was previously just given too much dark matter now is a viable parameter space. Okay, so for this part of the talk, let me just summarize that At low reheating temperature, we gain this independence on the initial condition for the freeze-in. We get this rich phenomenology because we have collider and direct detection bounds and also future prospect. And we have this, we can move from a freeze-in to a freeze-out regime smoothly. So we're closing this overproduction gap. And of course, this is also a generic framework. It's nothing especially related to the fact that we chose a scalar dark matter, right? Because the main feature is this Boltzmann suppression. And in fact, then we applied to other benchmarks with the Higgs portal, in this case for a fermion dark matter, and then for a vector dark matter, and also for a spin 3.5. But also after that, there were lots of work in many different other applications, and also from some groups, they also did lots of work on this low reheating, mostly applied instead to freeze out, which is also quite an interesting direction. I recommend you to have a look at those papers and many other papers that you can find on Inspire. Oh, apparently